But just as carbon dioxide, once it's in the atmosphere, has an influence for a long period of time, it also responds slowly to cuts in emissions. Methane doesn't stay in the atmosphere as long, but if we cut emissions, the climate responds much more quickly. So in fact, cutting methane emissions now is critical to trying to reach those targets of keeping the planet well below 2 degrees C, or maybe even 1.5, although that's getting almost impossible to see how we can do it at this point.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
The world needs evidence-based public policy now more than ever. Making the right decisions should not be partisan politics. Please help spread The Rational View by going to patron.podbean.com/The Rational View. Together, we can make a better future. Hello, and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. In this episode, I'm interviewing a researcher who's been studying the impacts of methane on the greenhouse effect and trying to assess whether burning natural gas, that is methane, is helping or hurting the climate. His most recent work suggests that it should not be considered an improvement over coal. And this may come as a surprise to many governments who've been using it as a bridging fuel to go from coal to greener, shall we say, options or low emission options, which have low carbon content or low carbon additions to the climate. If you enjoy what you're hearing, I urge you to press like on your podcast app, and I'd love to hear from you on my Facebook group, The Rational View. Robert Howarth is an Earth System Science and Ecosystem Biologist with a Ph.D. jointly from MIT and the Woods Hole Oceanographic Institution. He joined the faculty of Cornell University in 1985 and was appointed the David R. Atkinson Professor of Ecology and Environmental Biology in 1993. He's also an Adjunct Senior Scientist at the Marine Biological Lab in Woods Hole, MA, and is co-editor-in-chief of the journal Ocean Land Atmosphere Research. He's published over 250 scientific papers, reports, and book chapters, and has edited or authored 8 books. His peer-reviewed papers have been cited more than 85,000 times in other peer-reviewed literature, making him one of the most cited environmental scientists in the world. Howarth's research is broad-ranging and includes climate effects on nutrient pollution in lakes and coastal ecosystems, nitrogen effects in coastal marine ecosystems, sources of methane from natural gas operations in agriculture, atmospheric ammonia pollution, alternative energy policies and life cycle assessments for hydrogen, liquefied natural gas, and renewable natural gas. He is one of 22 members of New York's Climate Action Council, the group charged with implementing the state's ambitious climate goals laid out in the Climate Leadership and Community Protection Act of 2019. Dr. Howarth, welcome to The Rational View.
Thank you, Al. Great to be with you, and thanks for that long and generous introduction.
So, yeah, you've been in this role for quite some time. Can you tell me a bit about your background and how you got interested and got into this sort of field of work?
Well, as you say, I've been an Earth System Scientist, trained in oceanography, coastal ocean science originally, but a broad training in what we generally call the area of biogeochemistry, how humans and society interact with the chemistry of the world and how that affects the natural functioning of the world. You know, I was influenced by prominent ecologists or system scientists when I was an undergraduate, people who were doing world-breaking science on climate change, acid rain, DDT, things like that, involved both in the research world and the policy world. And I thought, that's what I want to do. I want to be a scientist who does creative work, but also has an influence on real-world policy. So I've been lucky enough to been able to do that all of my career.
That's very good. And you know, you look at the public opinion out there, and it's very polarized on this topic, as you might expect. There's definitely a whole group that thinks that climate scientists are in it for the money and are trying to get are lying to the public because of all the money that they're getting. So are you living high on the hog, Robert?
Yeah, yes, it's a great paying job. Yeah, no, I mean, I don't necessarily describe myself as a climate scientist. First, I'm an Earth system scientist who works on climate, among other things. And I've been working on how humans affect the environment and the climate in various ways pretty heavily since 1980 or so. And I've been teaching some on climate change since then. I got my Ph.D. in 1979, and one of my first jobs as a postdoctoral fellow was to help coordinate a multi-institutional course between Yale, Duke, MIT, and other institutions on climate change. So I've been at Cornell since 1985, and I've been teaching on climate change since then. So climate change is real. I wish it weren't. It's become much more of an imminent problem. It was even to me an abstraction up until a few decades ago, but it's clearly in our face now. It's not some long distance thing off in the future. As to the money, I gotta say that my research program would be undoubtedly better funded, more well supported if I had not stuck my finger into the policy arena around climate change repeatedly. It does make you a target. It does not help economically. Certainly, I don't make any personal money off of it, and it adversely affects our overall lab funding. In fact, you don't do it for the money. You do it because it matters. The climate crisis is real.
So you've recently been studying the impacts of methane on climate. And most people who are following this issue in any detail at all are aware of the physics of CO2 on forcing extra heat into the troposphere and warming the areas where we live. Could you provide a brief high-level overview of the physics of methane? Because this is a different gas than CO2, and it has a similar effect, but it's somewhat different.
Somewhat different and similar. As you say, the carbon dioxide and methane are the two most important greenhouse gases. And without a doubt, carbon dioxide is the most important. It's the single largest cause of global warming. But methane is the second most important. And just for context, the Intergovernmental Panel on Climate Change, the United Nations expert group that represents the global opinion of climate scientists, in their latest synthesis report, the AR6 report, which came out 3 years ago now, they say that methane is responsible for about 33% of all of the global warming that has occurred since the late 1800s.
Okay, so it's not insignificant.
It's not insignificant at all. It's really, really important. Now, how is it different and how is it similar in carbon dioxide? Well, they're both carbon gases. They're both single carbon molecule gases. Carbon dioxide's got 2 oxygens with a carbon. Methane's got 4 hydrogens with a carbon. Carbon dioxide is the most oxidized carbon compound on Earth, and methane's the most reduced carbon compound on Earth. So they have that in common. They're both greenhouse gases, meaning that they absorb infrared radiation when the Earth is heated by a sun's surface and heat is re-radiated to space. It's as infrared radiation, and the greenhouse gases keep that on our planet by absorbing that. Now, there are a bunch of greenhouse gases. Water vapor is important, but in terms of human-caused gases, carbon dioxide is most important. Methane's important because it's absorbing infrared radiation in wavelengths which carbon dioxide and water vapor do not. And so it's critical. There's nowhere near as much of it. There's 100 times more carbon dioxide in the atmosphere than methane. But methane is more than 100 times more effective in absorbing that infrared radiation because it's hitting wavelengths that carbon dioxide does not. So they're both important gases. The other thing to know is that they're both very active in various biogeochemical cycles. Carbon dioxide, once it's put in the atmosphere, it doesn't just stay there. It's taken up by forests. It's taken up by oceans. It's re-released from forests and grasslands and from the ocean. So it's a very active cycle. But the fact is, if we put carbon dioxide into the atmosphere from burning fossil fuels, some of that will remain in the atmosphere and have an influence on climate for hundreds of years into the future, perhaps 1,000 years into the future. Methane is different in that regard. We put it into the atmosphere, and it has a half-life of about 12 and a half years. It's oxidized in the atmosphere to carbon dioxide. Once it's oxidized, it's no longer methane. So with that half-life of 12 and a half years, if we put a pulse of methane in today, half of it's gone in 12 and a half years, 3/4 of it's gone in 25 years, and so on. It's dissipated.
Mhm.
So its influence is more immediate. It's larger per mass that goes in than carbon dioxide. We're putting less of it in. That's good. But its influence is nowhere near as long term. However,
Sure.
as I say, since the late 1980s, the IPCC tells us it's responsible for about a third of all warming. In terms of current warming, it's more important than that even, because we're putting a lot of methane in. The rate of methane emissions to the atmosphere are going up. And over the time period that, I mean, we should be worried about a lot of time periods, but a critical time period to worry about is the next decade to 2 to 3.
Mhm.
We've warmed the planet to maybe 1.3 degrees above the pre-industrial baseline. In Paris, back in 2015, the nations of the world in COP21 said we want to keep the planet below 1.5 if we possibly can, certainly well below 2 degrees C. The reason for that is that if we approach those temperatures, it's a very real possibility of runaway climatic warming feedbacks, that we reach the threshold feedbacks, which will irreversibly change our climate for the worse on the timescale of tens to hundreds of thousands of years. So we want to keep the planet cool. We are on target to hit that 1.5, perhaps in the next 3 to 5, certainly 10 years, the 2-degree mark in 20 to 30 year time period. So those next couple of decades are critical time periods for warming, and we need to do everything we can to reduce the warming. Now, reducing carbon dioxide emissions is a critical part of that. But just as carbon dioxide, once it's in the atmosphere, has an influence for a long period of time, it also responds slowly to cuts in emissions. Methane doesn't stay in the atmosphere as long, but if we cut emissions, the climate responds much more quickly. So in fact, cutting methane emissions now is critical to trying to reach those targets of keeping the planet well below 2 degrees C, or maybe even 1.5, although that's getting almost impossible to see how we can do it at this point.
That's a bit of a contentious statement, because I think politically speaking, a lot of NGOs have been pushing for natural gas as a transition fuel between coal and low emitting sources of energy. Now, I mean, we know that all of the sources of energy can be graded in intensity of carbon dioxide emissions or equivalent emissions. So there's coal is something like graded at something like 900 grams of CO2 per kilowatt hour, but natural gas is like half of that, is like 450 grams of CO2 per kilowatt hour in terms of its climate intensity. So a lot of people have seen that since it's half of coal, this is our bridge to get to whatever clean
fuel. Yeah.
So people are actually ramping up natural gas in favor of coal.
Well, they certainly have been doing that. I would have, personally, I think that's an old argument. 10 years ago, sure, a lot of people were making that, maybe even 5 years ago. I think most NGOs in the world have certainly walked away from that over the last 5 to 10 years.
Okay.
Certainly the science, I don't think the science supports it very well. And for the particular numbers you gave, there are a lot of parameters that go into that. So let's start with the direct combustion of coal versus natural gas. And when you look just at the combustion and you look at the carbon dioxide that's emitted, to get the same amount of energy, the carbon dioxide emissions are greater for coal than for natural gas, without a doubt. Not a factor of 2. Natural gas is probably, carbon dioxide emissions are about 64% those of coal.
Okay, and that's the direct emission from burning.
The direct emissions. Now, if you put it into units of kilowatt hours, then you're talking about electricity, and then you have to. Another aspect of that is what the efficiency of producing electricity from the heat energy is. And generally, people, in order to get the sort of numbers you're talking about, are assuming that coal plants are old and really inefficient. And of course, a lot of them are, and they're also assuming that the natural gas plants are new and very efficient, and some of them are. But there's a lot of variation. There are more efficient coal plants, there are less efficient natural gas plants. And so you need to pay attention to that detail. One of the things that's happened over the last decade is we have a lot of what we call gas peaker plants, which aren't plants which run all the time for baseload. They kick on when renewable electricity sources are low, for instance. And the efficiencies of the peaker plants are really quite low. They're lower than for the coal plants, which would work in the opposite direction of what you said.
So much of the capacity that's been added recently has been like in Germany to support
Water and
and
high efficiency plants
solar
run
and
for base load, but some of them aren't the peaker plants, and you kind of have to look at the detail. But the other aspect of it in those calculations is the consideration of methane. And a lot of the original arguments, this idea of gas as a bridge fuel going back 15, 20 years ago, completely ignored methane. They've done so less in the past, but they've often underestimated methane. Now, you can't use either coal or natural gas without having some methane emissions to the atmosphere. But the fact is that methane is a contaminant of coal. So when you mine coal, you do get some methane to the atmosphere. Natural gas is methane.
Right.
95% of it is methane. That's just what natural gas is. And it's impossible to develop it, process, transport, store it without having some of that emitted to the atmosphere. And it turns out that if you just have 1 or 2% of the production of the gas emitted unburned to the atmosphere, because methane is such a powerful greenhouse gas, that makes the greenhouse gas footprint of natural gas at least as bad as coal, maybe worse than coal. So it's not just carbon dioxide.
1 or 2%.
Coal is worse in terms of carbon dioxide. Natural gas is worse in terms of methane. And the latest data. I published a paper with Tony Ingraffia and Rene Santoro on this back in April of 2011, saying, wake up, people. This bridge fuel idea may not be true if we fully considered methane. And at the time we published it, it was a speculative paper. We said so publicly. We said so in the paper because there really wasn't good data available on how much methane was emitted from using natural gas.
Right.
We used the best data that were out there. Or no peer-reviewed papers at all, particularly on shale gas, the fracked shale gas, which is new at that time. So we used the best information we could find. It was unpublished information from industry sources, often poorly verified, unpublished stuff from the U.S. government, also poorly verified. So we put out this paper and said, using the best information we can find, the methane emissions offset the carbon dioxide advantage for coal. Natural gas, shale gas in particular, is not a bridge fuel. But of course, we need better information on it. And I got to tell you, I think maybe the biggest accomplishment in my science career that I'm happy about is I said scientists have to go out there and measure methane. And again, our paper came out April 2011. There were no peer-reviewed papers on methane emissions from shale gas at that time. There are now more than 1,800 papers on this in the peer-reviewed literature. The best data are coming from satellite observations and airplane flyovers. There's a paper published in Nature last March that summarized the most recent literature on that point in time. They said that we now have almost 1 million observations.
Wow.
That are well documented. So Earth's changed since our paper in 2011. We helped spawn that, and I'm very proud of that.
That's some good
the information that's available is that the emissions are they're well above 2%. They're 2, 3, 4, 5%. And so we now know that, in fact, natural gas is at least as bad or worse for the climate than coal. Now, whether it's worse or not depends on the time frame we do the analysis on. Because if you want to compare carbon dioxide and methane emissions in terms of their carbon climate, you need to assign a time frame to it. And the carbon dioxide has a longer influence than methane. Methane is more potent in the shorter time period. And historically, governments have used a 100-year time period after a pulse emission of methane to compare it. And what that does is, the methane's gone by 100 years. And so you're averaging in no impact over at the end time period, as opposed to a really high impact early on. And it downplays what methane really does. If you use that value, then methane doesn't look anywhere near as bad as the IPCC tells us it is. So, many of us have been saying, let's use a shorter time period. 20-year comparison is better. And if you use a 20-year time period with the methane emissions we know are there, then natural gas is worse than coal. If you use a 100-year time period, maybe natural gas is better than coal. But I think that would be the wrong time metric to use. It's not a bridge fuel in any regard.
So you have these good observations now that show that we're leaking methane, and I've seen people looking at maps, geographical maps, and showing hotspots of methane emission over fracking fields, for example,
right?
Where you fracture the rock and it just bubbles up from the ground. And this is something that hadn't been taken into account in previous models and plans for building all of this natural gas infrastructure. So yeah, that's a little bit frightening. So you would recommend that natural gas not be used as a bridge fuel at all? That we just
Yeah,
move away from that entirely?
move away from all fossil fuels to begin with. I mean,
Sure,
I hate.
sure.
I've written plenty of papers comparing gas with coal, LNG to coal, et cetera, et cetera. And I mean, it's one metric to make the comparison, but we know the IPCC is telling us, global leaders are telling us that if we want to have any chance of reaching the COP21 climate targets, if we want to keep the planet well below 2 degrees Celsius, we need to be living in a world that's free of all fossil fuels by 2050 for sure, probably by 2040. We need to cut our use of fossil fuels in half between now and 2040. And so, it's despite the fact that I, among others, have written papers saying, one's worse than the other, we got to get rid of both pretty quickly. And we need to be moving into solar, wind, hydro, energy storage, high efficiency technologies of heat pumps, electric motors for transportation. That's the energy future we need. There's no room for either coal or natural gas. But if I had to choose one versus the other, I personally would get rid of natural gas faster than coal even.
Wow.
Not that I like coal. It's nasty fuel. Got to get rid of it. But
Interesting. Yeah, I mean, it seems though that most of the energy companies are the fossil fuel energy companies. You see their advertisements. Go for solar, go for wind because it needs natural gas. We work hand in hand with these things because obviously the battery situation just isn't there to support the on and off fluctuations of these things.
Well, let me back you up there a little bit. I mean, if you look at what the oil and gas industry's been saying over 50 years, they've known about climate change, and they've known about methane too, by the way, going back to at least for climate change generally to the 1950s. For methane and its role certainly since the 1970s or 1980s, they were well aware of it. They kept it secret. They downplayed climate change. They denied climate change. They said they weren't the players. They've moved away from doing that now, and they've moved into this realm, as you say, of we can move towards renewables, but you need natural gas as to help. Originally, they said as a bridge fuel away from coal. Now they say you need it as a sort of a peaker use when the wind's not blowing, when the sun isn't shining. That's not actually true. You said the battery technology is not there. The battery technologies are there, and they're getting better all of the time. Engineer at Stanford, Mark Jacobson, and I and others published a paper back in February of 2013, originally focused on the state of New York, but we came up with a blueprint to how to move the state of New York to a fossil fuel-free future from the 2013 time period, so more than a decade ago, and do so in a 20 to 25-year time period using technologies which were available at that point in time. Batteries are a hell of a lot better now than they were then, but the technologies were available and cost effective to do it more than a decade ago. It's even more so now. Now, are we deploying batteries fast enough? No, we're not deploying wind or solar fast enough either. But the cost of batteries now is 10% of what it was 10 years ago. They're getting cheaper and better all of the time. And we need a couple of nuances there too. Batteries, by say lithium-ion batteries, are one way to store energy, but there are other ways to store energy. You can store electricity with pumped hydro stations, for instance. We've been doing that for decades. You pump water uphill when you have the electricity in surplus, and when you need it again, you let it run downhill and run it through generators. So that's a form of battery. It's not an electrical battery; it's a physical battery. There are a bunch of other technologies of that sort, but there are also other ways to store energy, and there are better ways to manage it. Let me just go to the other storage. I heat my home with a heat pump. It's an old 1890s farmhouse, and we converted from oil to a ground source heat pump 10 years ago. And so I need constant electricity to run that, particularly in the winter. It's quite efficient. I use a fraction of the energy I used to, and my emissions are zero, but it still requires electricity. So what do you do when the wind isn't blowing or the sun isn't shining? Well, one thing we could do, and I haven't done it yet, but it's entirely doable, is to increase the thermal capacity in my home. So that, say, during the day when the sun is shining, I'm running my heat pump that doesn't necessarily just heat the house, it's heating a thermal mass. And then at night when the sun's not shining, I can draw on that mass. So thermal energy storage, in addition to electric storage, can be part of the key. There are new technologies that are highly efficient at thermal storage on short time periods and seasonal and annual bases. They're less expensive than battery electric storage. And I think that's a big part of the future. And that's sort of hinted at part of what I was, in addition to the storage, there's a whole issue of demand regulation. Instead of having my heat pump just say whenever the thermostat says it needs a little heat, manage it so it's drawing electricity when the electricity can best supply it from the grid, and have some buffering in terms of heat. And you can do the same thing with people charging their electric vehicles and many other things. So through proper managing of the grid and some battery storage and a lot of thermal storage, we are well prepared today to have a energy system that requires no fossil fuels.
I mean, I hear what you're saying. I think the stuff that Jacobson was publishing 10 years ago has been very optimistic in terms of the battery availability. Currently the world's battery availability is enough to back up a grid for like an hour at most, sure. Right? I mean, grid scale battery just doesn't exist. Certainly battery is a good replacement for peaker gas, I think. Yeah, but I don't think it gets that sort of seasonal lull problem that we have with a lot of the batteries power supplies. Don't.
But thermal storage could, and there's I don't remember the exact location, so forgive me, but I think it's in Saskatchewan, maybe Alberta. There's a new major housing development that relies on their winter heating totally from thermal storage from the summer.
Geothermal,
not electrical storage, it's thermal storage. They use solar to heat, underground aquifer in the summer and then pump it back out. That's a cold climate. If you can do it in, I forget which province, so forgive me, my Canadian friends, but if you can do it in either Saskatchewan or Alberta, you can do it many places.
Yeah, and that's, with our latitude, there's not a lot of sun.
Yeah. So, and different places are going to need different solutions, but you can also use wind power to generate heat, which could be thermally stored. Thermal storage is easier long-term than is battery storage. But it isn't all just about batteries. It's more nuanced than that.
Yeah, I think in Ontario, at least, we're doing quite well with nuclear power, and bringing up the sort of reliable power supply that we need to kind of go through our long, dark winters when the sun isn't shining and the wind isn't blowing. We have, unfortunately, here in Ontario, we have a problem with our high wind production is out of phase with our high load peaks in winter and summer. We have shoulder season wind and summer and winter electricity peaks. So we're not
I'm in the Finger Lakes of New York, which isn't that far from you, and we've got the same problem. So I hear you. You need storage. I'm not a huge fan of nuclear moving forward. I could just digress on that a little bit. I'm on the commission. We call it the Climate Action Council for the state of New York, but set up by state law to develop the implementation of our climate law. And there are 22 of us on it. Majority of the members work for the governor. They're commissioners of various state agencies and all hardly radical people. We had to come up with a detailed plan to make our climate law work by December of 2022, so a little bit less than 2 years ago. And we spent a fair amount of time debating nuclear energy. We have several nuclear plants in New York, less of our power by percentage than you have in Ontario, but still significant. Maybe 25% of our total electric power right now comes from nuclear, 25% from hydro, by the way. And we argued, we concluded, argued's not the right word, we debated and concluded that it made sense to keep the nuclear plants we have going as long as they're safe and operable and within their standard. But making new nuclear plants, we argued against as a commission. And the argument, we didn't even debate safety and all the issues one might. It was simply efficiency and an economic argument. And we said new nuclear power plants are slow to deploy and expensive to build relative to new hydro, new wind, or new solar, and the appropriate storage, including maybe thermal storage and those things. So on the basis of pure economics, we said nuclear is not the way to go in the future.
I think that argument has a lot of holes in it, though, because I think we've looked at, people use the levelized cost of electricity to show that it's very cheap to throw out solar panels and wind turbines, but the backup system that allows you this sort of long-term, it actually brings it up, above or comparable to new nuclear. And we're, in Ontario, at least, we are refurbishing our CANDU plants on, below budget and on time. So
Yeah,
if you look at,
I've seen that. We can, let's leave it there. Just to say, at the state of New York, we've made the opposite determination. But a lot of it has to do with, you're right. If you look just at the cost of solar and wind deployment, you do need to look at the storage and all. But it isn't just electrical storage again. And if you start realistically thinking about thermal storage and demand management, it changes fundamentally.
I certainly like thermal storage as an idea. I mean, I think pumped hydro is good where you have the geography to support it. But I think we're mostly tapped out in a lot of our hydrological energy resources, but the thermal is definitely something worth looking into, I think. But you guys shut down Indian Point, right? You had I
didn't. The state did, yes.
and most of that became natural gas, didn't it?
It did, yes. Yeah. Unfortunately, and hopefully that's a temporary blip, and we're working hard to increase our wind and solar. And we've also, the state of New York has a long-term contract with Quebec Hydro, and we're building a high capacity DC transmission cable from northern Quebec down into New York City, down the Hudson River, which will they'll make up most of the nuclear from Indian Point. But you're right, short term, until we get the other things on board, it increased our gas use a lot in this state.
I appreciate you're coming to chat with us about this. So you believe that natural gas is not something we should be looking at. I mean, that's the summary of your research, is that the methane is leaking too badly from all the sources of natural gas, that
from the production and the supply and processing
at this point in the environment,
making it worse than coal. Let me just add two caveats. That one is you've referred to leakage, and of course there are leaks, but that that makes it sound like it's a poor pipe, and you just do a better you get a better plumber in there or something, right?
Yeah.
A lot of it's purposeful emissions that are part of the operation. So, for instance, when you pressurize a gas pipeline and put the gas to market at high pressure, for the most part, the compressors that are pressurizing that burn natural gas to do so. They do so fairly inefficiently, and their exhaust stream has a fair amount of methane in it. I wouldn't call that a leak. It's an inefficient burn. When you go to do maintenance on a high-pressure pipeline, you can't weld on a pipe that's full of methane. It's explosive. And so the gas in the pipeline is released to the atmosphere before you do maintenance. That's called a blowdown. That's not a leak. It's not an accident. It doesn't happen every day, but it's a routine part of the management of the thing. So, the best data suggests that, again, somewhere between 2.5–5% of the gas that's produced is emitted unburned to the atmosphere. At least half of that is part of the purposeful operations. Half of it might be leaks. So we can tighten up the plumbing and all, but we're not going to take it to zero without fundamentally changing how we think about gas. And to me, given that we have to move away from all fossil fuels by 2040, let's not waste too much time reinventing how we handle gas. Let's use those resources to move to non-fossil fuels.
Well, thank you for spending your time and chatting with us. I appreciate getting your insights into this. I know you're very busy, so thank you.
Appreciate the chance to talk with you.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/therationalview. Thanks for listening.